great.
Okie dokie. So, hi everybody. Now that we've got everything working again, today we're going to be talking about machine learning inference at the edge. So brief introductions are in order. My name is Austin Blackstone. I'm the developer evangelist for ARM. I work on the ISG side of the house, so IoT software is my specialty. Specifically, I'm responsible for the Pelion platform, which is our giant online cloud thingy-majigger that does everything you ever could wish for, and InVidOS, which is some software that runs on Cortex-M devices. If you'd like to know more about those, I was told to explicitly not make this a sales pitch. So if you want to know more, you can ask me questions at the end, and that's how I can get around that. That said, I am an engineer first. I am not sales, I am not marketing. If you would like marketing, I've got my two guys at the back here. Guys, raise your hands. So these guys know everything about the sales side of the house if you have any questions. And I'm kind of a jack of all trades and master of none. I'm dangerous enough that they put me on stage and assume I know what I'm talking about. But as you will all discover, I am just one of you. So that said, today we're going to do a 30-minute overview of machine learning at the edge, specifically inference at the edge. I'll get into the differences there. Then we're going to have about 30 minutes of hands-on workshop. We've got some boards up here at the front that we can pass out and get around. I've got 21 boards, and I think we've got more than 21 people, so some people might have to share. I sent everyone who signed up for this ahead of time an email, so you should have gotten an email with some links for some things to install. If you can, go ahead and install them. That'll give you a good idea of how the tool chain works and how you can also use machine learning at the edge. If you didn't, you can do it now, or you can not worry about it and just ask lots of really good questions. I'm totally down for having really good discussions or really hands-on workshops. We can take this however you all want to go.
Who did the email come from? What email address did the email come from?
It would have been austin.blackstone@arm.
Sent at 1 o'clock in the morning on the 23rd.
Yesterday.
Yeah, it's really confusing because it's like tomorrow we got it at 1 a.m. Like which day are we talking about?
I was sitting at the airport in Seoul in Korea, so I was kind of guessing too.
Wow.
I wasn't really sure what day I was on anymore. And so yeah, if you haven't installed it, please do so. That said, a little bit of a heads up on what we're going to be doing. My initial intention was to show you how to deploy models at the edge, then how to send training data up to the cloud, how to train new models, and then deploy those models using firmware update. That was my intention. And then I got super sick for the last 7 days, and all of that went right out the window. So we're going to be talking about how, in theory, it's possible to redeploy models at the edge, and in practice, I will show you how to actually run models at the edge. Sound good?
So,
You had a question?
if we didn't get the email, can you put it up on the screen or the whiteboard how to download that, or?
Yeah, so if you just Google install embed CLI,
Okay.
the instruction should be like the first or second link that pop up. And it'll take you to os.embed.com/whatever and say if Windows, if Mac, if Linux, or the instructions. The keyword is install embed CLI. Also, if anyone's familiar with Python, you can just pip install embed-CLI. Any other questions? Cool. Right, so when I say machine learning, actually before I say machine learning, who in here knows the difference between a microprocessor and an application processor? Okay, 1, 2, 3-ish, 4-ish. Okay, so I'm going to define a few things there so we've all got a common terminology set so that as we go forward, we've got some common understanding. So microcontroller means a small embedded system, usually headless. It runs in terms of megahertz. Application processor is in terms of gigahertz. It usually can run Linux or Windows or things like that because it has an MMU, and MCU cannot. So your phone, your laptop, those are all application class processors, big beefy boys, usually a couple of large cores that run super fast. MCUs are the things that are in this webcam, in that clock, in that projector. They don't run nearly that fast because they don't have to. They're usually digital unitaskers. You put an RTOS on them. You do not run Linux on them. They are very small. Order of magnitudes cheaper, order of magnitude less power, order of magnitude more of them in existence. The majority of, when we talk about IoT, is going to be driven by these small microcontrollers that are just going to be deployed everywhere. Because the whole premise of IoT is it's one leg of the fourth industrial revolution. You've got IoT sending sensor data to the cloud, big data collecting that data, and then AI making sense of that data to leverage those multiple data streams to be more than the individual data streams are worth. Everyone follow me? IoT produces data, Big data stores data, AI computes that to derive new value from. Savvy? All right, so when I say machine learning, for the past decade, 2 decades-ish, machine learning usually meant large servers, big expensive cloud clusters, massive GPUs that could lightning fast process data, and they were usually thousands of dollars to set up. So machine learning for the longest time has been in the cloud, in data centers, and that's all you could have. Because to process all of that massive amount of data that you store with big data, we needed big computers. This is by and large still true, but increasingly we're seeing, as we move forward, it being pushed out to the edge. So now you're seeing people talking about running machine learning inference at the edge, processing the data at the edge, using machine learning at the edge, running on these smaller devices. There's a way to do this, and it's currently the bleeding edge of what's possible, and that's what we're going to be talking about today. So with the MCUs, they are smaller, they are cheaper, they are more power efficient, but that's because they're slower. They're super memory limited. So when I say an MCU, I'm usually talking kilobytes of memory space, megahertz of processing power. Traditionally, all of this machine learning stuff, to train it, you still have to train it in the cloud, and to run it, some of these models can be hundreds of megabytes to gigabytes in size. They're not going to fit on these tiny devices. However, the thing we're going to be talking about today is how to take these massive models and run them on these tinier devices. So why edge computing? Why do you care about running these things out on the edge? This is mostly because of the reason you want to run it on the edge can vary, to be honest. Sometimes it's a legal reason. Sometimes you don't want to send data all the way up to the cloud. HIPAA compliance for things like healthcare data. If it leaves the device, all of a sudden there's all kinds of legalities you got to deal with. Sometimes it's your power budget. Wireless transmission is super expensive, and if you've got a small embedded device sitting on Wi-Fi, the amount of power it takes to wake up, read a piece of sensor data, and then determine if it's valuable enough or not is a couple of microamps. But as soon as you start transmitting, you're talking about milliamps. So to send that data up to the cloud is super expensive, especially in sleepy devices. Furthermore, these devices are going to be everywhere. So the amount of computing power that's actually going to be out in the field when we see IoT deployed in mass over the next decade, there's going to be far more computing power out and about in the fog layer and the edge layer than there actually will be in the cloud. Yeah, that's really why you want to do it, both for cost and for just raw processing ability that would otherwise go wasted. So microtensor is the thing we're going to be talking about today. Microtensor is this embedded library that allows you to take these models that exist in gigabyte size and shrink them down using quantization to run on these small embedded devices. Today, it works with TensorFlow. Who in here has heard of TensorFlow? Okay, cool, it's about half of you. For the other half who have not heard of TensorFlow, TensorFlow is one of the main methods of training models. So when you take all that data from big data, you've got to then process it to turn it into this graph that is the model. TensorFlow is the Google product that enables you to do that. They just released an update in TensorFlow 2. It's now super easy to use. There's also products like Caffe and PyTorch and all these other things. Depending on what tool you choose to use to train your graph, you will then get different output file formats. We chose to first support TensorFlow's protobuf files. That said, it's easy enough to add exporters for Caffes or PyTorches or anything else. But first and foremost, it was a small team and we had to make a decision, and we decided to work with Google's format. So today, it supports protobuf files. If you have a need, we've got some really good documentation on how to add importers for other file formats. Because at the end of the day, it's literally just taking a graph with a bunch of weights and node values and translating it from one size to another. That's all it is. Today it runs super small, less than about 130K of RAM. So we're not talking super, super tiny embedded devices like the child's toys you get, but we are talking a moderate sized device. For reference, if you are creating an embedded device that is hooked up to the internet, you're at least talking 126 to 256K of flash and equivalent spaces of RAM. That's because things like networking stacks, you gotta have flash storage for doing your firmware updates, usually twice the size of whatever you want to store. Because of those considerations that come on, and security certificates. God, I hate security certificates, they're so big. Because of that, usually you'll have a device that can handle 130K of flash at a given time, even if it's just for a spike and then you unload it out of memory. So this is not unheard of for an IoT device, just to give you a point of reference. That said, one of the really cool things, I think it's the next slide. So when you're running a neural network model, who in here has trained a neural network before? Okay, 3, 4, okay, cool. So I get to explain this. I'm always excited about this. So a neural network really is just a networking graph. It's points that are then connected to other points. And one of the things that a lot of people don't understand is that a neural network can be input at any point and output at any point. They are not a one-way flow. They are not necessarily linear. In fact, usually they're compounding and they hop over different layers to talk to each other. So for example, I could put in data right here and then read it out right here. Or I could put in data down here and then read it out right here. Where I define my input and where I define my output is a function of the training of that graph. It's a lot of graphs that you'll see will actually have multiple different things that you can do with them. So for example, here, I put in dog at x1. So I put in an image, right? That image goes in. And then depending on where I read it out, it might read out as dog. Or if I put a different image into the left, it might read out as cat. Notice that these are coming out of 2 different nodes. So this network can recognize 2 things. It can recognize whether a picture is a dog or a cat. And depending on where I pull the node out, will tell me which one it is. Follow? It's not a single input to single output. It could be, but it could also be multiple input to multiple output. It's one of the beautiful things about neural nets.
Is on your output, in this context, in microtensor, or in this embedded space, are we still dealing with percent hits on dogness and catness?
So it depends on how you train your network.
Okay.
You can train it so that you have a single thing, a single node, and the output says dog or cat, so it'd just be a tuple. You could train it so that each of these puts out a tuple that says dog 20%, cat 70%. That's entirely up to how you train your network and how you input your training data.
Thanks.
Cool. Any other questions before I go ahead? So big takeaways, it matters. Your training will determine what your network looks like, and it matters where you put it in and where you take it out. There isn't a single endpoint or a single outpoint. There's multiples. That's going to be important later. Right, and then these are the weights that are assigned in your graph. I'm going to show you guys a really cool video here, because I can't actually show you the demo because I don't trust this equipment to work. Let's see if this will work for me. So today, the thing that we are going to be building it's going to look like this. So, what's happening right here is he's drawing a number on the screen, pressing the processing button, and then the model is recognizing the number. So he's going to do it again, reset the board, draw another number onto the touch screen, this time 8, press the button to run recognition, and the model puts out 8. So this is what we're going to be working with today. After this presentation, that's what you're going to be programming, just to give you some context. What this was the MNIST data set, which is a common data set that's used in machine learning. I forget what MNIST stands for, but it's essentially a bunch of handwriting data sets, well over 1 million samples, where they literally just had people write the numbers 0 through 9. We then train that data, and we train based on the data, and then we come up with a model. That model we then load onto the board, and then when we take the screen's input, we shrink it down to be a 128 by 128 graph. We'll run it through our network that we trained, and then pull out the number on the other side. So that's what we're going to be doing today. So microtensor specifically is interesting in how it works. I want to emphasize that microtensor and the embedded inference that we're going to be doing today is not the collecting of your data. It's not even the training of your data. Before you can do machine learning, you need that big data somewhere. So you can't just suddenly decide, I want to run ML on my processor and then have it work. You got to spend the time to collect the data, catalog the data, and label your data. So you have to have that picture of 0 through 9. You have to have tens of thousands of each of them, and you have to have them labeled saying, this is a 0, this is a 1, this is a 2. It takes a lot of time to train it to label your data and collect your data. You can think of it like the problem that you want to solve for. You've got to have 10,000, 100,000 examples of that data, plus or minus a little bit of fuzziness, and you got to have the box drawn around it just right. So when you create your algorithm, it knows what it's looking for. If you draw that box slightly off so that you're clipping your data out, or you've shifted it over so the thing you're looking for is over here and your data shows something over here, your algorithm is not going to be terribly specific. So I really have to emphasize that getting good data, and more importantly, labeling that data, is as critical to machine learning as the training of the graph itself. If you start with terrible data, you're not going to have a good algorithm. That is the thing that's overlooked way too often. If you want to use ML, if you want to do production with ML, you've got to invest the time to either buy the data set from someone, or more likely today, build the data set. And that is something that you really got to plan for. Next, you got to train your data set. You need a machine learning specialist, also known as a data scientist. These are people who have a background in stats, and they are really, really good at spending way too much time toiling over these graphs and tweaking the different parameters that you've got and trying to figure out how it works. Then once you've got your graph output probably comes out at, we're talking gigabytes when you pull it out the first time. If you want to run that graph on a smaller device, you got to shrink it down. That's where microtensor comes in. That's what we're talking about today. So we're not going to be talking about labeling your data. We're not going to be talking about training your graph. We're just going to be talking about taking an existing model that's way too big to run on these devices and shrinking it down to run on them. So microtensor does a really good job of generating C++ code from these massive graphs. It does this through a process known as quantization. The TLDR on it is most of these larger graphs that are output come out in 32-bit weights. Turns out you don't need all 32 bits to really maintain your data integrity. You need 8 bits. So through a process called quantization, which is really just a fancy way of saying strip out the extra data that you don't really need, we can shrink that graph down to be much, much smaller. So that's really all that microtensor does. Takes in a protobuf file, outputs a .c and a .h file, and does quantization to strip 32 bits down to 8 bits. There's a little bit of accuracy loss when this happens, but on average it's about 1 to 1.5%. So it's within that margin of error, and if you get your training data correct, it's all bueno. Any questions so far? I do want to emphasize that the code that comes out of microtensor, I'm going to be talking about it in the context of ARM-MIDBEC because that's the company that employs me and it's what I know first and best. But it is not specific necessarily. It is a straight .c and .h file. Anything that can compile that can use it. We run it on our Mac laptops. I've run it on Edge Linux gateways. Wherever you want to shove a model, if it's too big, you can shrink it down so it can run there. Okay, savvy. If you're interested in how it works, this is a base overview of it. That process I was telling you about called quantization, it essentially takes them and as it moves through the graph, readjusts those 8-bit values, essentially giving it an offset and an index. If you have a 32-bit value, you give it, was it -1,000 to positive 1,000, roughly, plus some bits in between. It turns out that on a absolute scale, you still have to represent that data. But if you shrink it down through quantization to be relative, so between layer 1 and layer 2, if you have an index offset that says, oh, we're only talking between like 25 and 60 here, then you can give it an 8-bit value relative to that offset to then shrink that down so you can really compress the values down. So instead of talking about absolute offsets, we just take it and talk about relative between the two layers. And it turns out mathematically that works, and it's a great way to save a ton of space. You wind up with TensorFlow models that look like this. This would be like our input, the Y prediction value that would then run through everything. On the inside of things, we've got a whole bunch of different tensors that we're running. Does anyone here know what a tensor is?
Three-dimensional matrix?
Yeah, more or less. It's a fancy math term for a weight and a node. Essentially, if you took graph theory in college as an electrical engineer, it's basic graph theory with weights and nodes. They just chose to use a different word for it because they're math nerds and they had to choose something that wasn't domain specific. But yes, as you get into more complex graphs, they tend to take on multi-dimensions. One of the really cool things to note is that we're talking code gen here. So this is completely platform agnostic. Code gen means you're not vendor locked in. You want to take this, you want to walk somewhere else with it, you own it. That's all it is. It's just a generation tool. There's no custom system lock-in, so you can all use this thing or that thing. There is no custom proprietary algorithm that prevents you from ever going anywhere else. It's literally just taking it from one format, transposing it to another format.
Does the generator have target architectures you can point it to?
Yeah, yes. So depending on how you run your compiler with it, that's actually where most of that comes in. It is fairly agnostic. So when, back in here, when you then compile your .c and your .h into whatever system you're using, you compile it at this stage to run it on hardware. It is completely agnostic of the underlying hardware itself.
So when you go to actually compile it, your compiler may throw warnings and errors still.
Entirely possible.
There's no guarantee that the generator tool will actually be compatible with the given embedded system?
It's fully compliant with C++11. It uses all the standard types. So
Okay.
as long as whatever you're compiling for supports C++11, it should just work.
Cool.
We do run it in a massive CI against several different node systems to make sure that we're not accidentally introducing anything that would break that. Oh, here's the slide I was looking for. So the quantization, again, shrink it from 32 bits to 8 bits, very little accuracy loss. The big thing that this enables you to do is run these large graph flows on much more constrained devices, today Cortex-M devices. For the memory management side of it, this is actually really cool. Because we're a bunch of embedded system geeks, we swap out exactly what we need. So if we've got, say, a 4-stage neural net, we're only evaluating one stage of that pipeline at any given time. We load up stage 0, we evaluate what we need, unload it, load up the next stage, run through it. So we're not actually loading the entire graph into memory at any given point in time. It all exists in Flash somewhere, because you have to have your weights and your nodes somewhere, but the actual RAM usage that you're utilizing at any given time is at most one width of your graph. That's it. So one depth size. That's how we can run it on these super small devices where maybe you don't have, if your entire graph is 256K in Flash, store it on SD card. And then you only have to use, say, 32K in RAM at any given time to run through that graph. That's where it comes to being really powerful for embedded devices. So you can run in place and swap the data out in the same memory cycle. One other thing to point out, we have multiple different tensors for embedded devices. If you use EmbeddOS, we support multiple different storage types. So you can run it straight out of RAM. You can run it from an SD card if you don't mind the slight latency delay. You can even run it from a network location, because the thing that underlies all of it is just using the file system abstraction in EmbeddOS, of which there's the internal flash, the internal RAM, external flash, NAND flash, all the different storage types that you usually get. And we have even a network storage type supported. So if you want to offload it into your gateway and just pull it down from your gateway as needed, you can do that. All really, really fun ideas. So some use cases for these things that we're going to see today. One of them that exists is in low power WAN. So things like LoRa. Who in here has messed with LoRa before? Cool. So you guys know about the super low bit rate limitation that you have, right? Imagine if you wanted to transfer an image across LoRa today. That's super non-trivial, right? You would have to wait probably 2-3 hours to get a 128 by 128 image across that thing, depending on how busy it is and what bandwidth limiting you've set, and if you're a Class A or Class C device. But it still takes time to send things across. What if you compressed it using an ML algorithm? So instead of sending the high format 4K image of our little mushroom friend, you just send a rough representation of it. Because that's really all you need at the end of the day, is to know what is roughly there. You could write an ML algo that does that. Have it on both sides, decompress it back through. This is one of the primary cases that we've seen. Another one that we're seeing a lot of interest in on the edge is sensor fusion. So taking existing cheap hardware and making it better through software. Think of software value add, so that if you had 4 or 5 20-cent temperature sensors, all of a sudden through ML, you can make them perform like a $50 temperature sensor. That's the pitch. That's the whole value add that ML has. You get enough data on these things, you crunch the numbers, you get a better algorithm. Yes, sir.
You mentioned images. Would there be really any difference between image and, say, sound recognition, categorizing what that audio is?
No, not really. Keyword spotting is one of the big ones that we're seeing on embedded systems at the edge. So today, the way that the Alexa and the Google Assistant work, depending on which engineer you talk to, is it sends a constant audio stream out to the cloud, and the cloud then processes that audio stream to do keyword spotting, and then sends back down a flag saying, hey, keyword spotting. Well, what if instead of doing that, you were able to do it entirely on the edge device, so that it didn't have to talk to Wi-Fi? Well, then suddenly you could have Amazon Dash style buttons that are entirely battery powered, which is right now completely unheard of. You can't do keyword spotting for those devices, they all have to be plugged into the wall. So keyword spotting to do that is one idea. Another idea is voice control of some of these simple IoT devices that we're seeing. So instead of having to reach for your phone to turn your Bluetooth lights on or off, you just say, hey, lights on, hey, lights off, something like that. We haven't really seen the pull through with it because we're still in the super early days of ML. So if you've got an idea and you can get the data set and you can make the algorithm, the world is your oyster for the data. Any other questions? No? I see a lot of semi-confused faces and a lot of people kind of zoning out and a few people thinking. Okay, cool. Okay, so let's get coding. Who in here has Embed CLI installed? Cool, you get a board. Come get a board.
I think it's installed. Oh yeah, definitely.
So, just to be clear, these are loaner boards. I don't have the budget to give them away, my apologies. So at the end of the workshop, please do make sure that they make their way back up to me. Feel free to just crack them open, take one. I've got some USB cables in here as well. You will need a board and a USB cable. How much does it cost? $75 each. That's why I can't give them away.
So do you think that
This is from your GitHub website. And so you want us to return this?
Yes, ma'am. I need them returned so I can run this exact same workshop next time.
And,
I know.
Well, no, my computer's the same way.
Okay,
So like the DigiKey that I wrote this morning didn't work on my laptop because I don't have USB rights. But I was able to do a different board later. Your words, no.
So fair enough, we're gonna find out. Here, you can look at all of them while I go find the cable. That's the micro USB I sent you. So plug it in.
This is what happens if you make multiple levels of orders.
Oh, actually, yeah, that's right, I'll need that. This is,
That's not on board. I apologize. You got a cable?
yeah, it's probably, because he just
So MWS is, when you do
yeah, they're just designing. They in fact designing the, what do you call it,
okay,
the
so
instruction set.
here are the instructions. Go ahead and open up this GitHub page. This is from the Microtensor open source project page. It's going to have the instructions to walk you through the workshop. I'm going to walk around the room and make sure that everyone's on the same page. Once everyone seems to be clicking along, I'll come up and show you how to run through it. So those who have an intuitive knowledge of how to do embedded systems, jump on it and then help me teach everyone. I should note that today we're using Embed CLI, so it's a command line interface. If you can give me 3 to 4 weeks, I'll have it all working in our Embed Studio, which is a GUI editor, and support eventually in our online compiler system. We are on the bleeding edge, so we get to use the command line. As soon as things get a little bit more mainline, the tools will get better, obviously. So there is that
Nothing's better than the command line.
I completely agree with you. Unfortunately, my boss and my boss's boss completely disagree with us. I like to be able to script all the things.
Yeah.
They want it to be one click easy. So go ahead and do that. Once you've got embed CLI, it's going to be a simple embed import of the project link. Who wants me to show them how it works? So 2, 3, 4 guys. Who wants to do it on their own and then try and fail and then have me show them how it works?
So should I expect the embed import to just kind of hang here at the embed OS?
Yeah, it'll take a couple minutes. It's embed OS is about 250 megs, so it'll take a hot second to download this Wi-Fi. So it seems like we've got about split hands. About 5 people want it, 5 people don't, and everyone else doesn't care. So I'll just go ahead and show you how it works if that's cool. So, where's my terminal?
Terminals are for the weak.
Terminals are for the superior engineer.
You're young.
Bold words, I know. Let me get that off the screen. Let me see. So, you're going to run something that looks like embed import
Where do you have to do that from?
the command line. So if you installed embed CLI, you should have this tool
Oh,
installed.
you have to.
Yes, ma'am. That was one of the prerequisites. If you do not have the tool installed, then just run. Now, you're going to have to do pip install embed-CLI, and you're also going to have to install GCC, ARM node EABI GCC specifically, not the latest release, but the release from 6 months ago. It's why if you search install embed CLI, there's a page, and it has all the instructions on how to install all of it locally for Windows, Mac, and Linux. There's also simple installers for Windows and Mac. If you're on Linux, we assume you know what you're doing. If you're on Linux and you don't know what you're doing, please move over to OS X.
Ooh, that was a burn.
I'm just saying, if you're on Linux and you don't know how to use it, you probably shouldn't use it.
And
Right,
use
so
a Mac.
Macs are almost idiot-proof these days. It's great.
Exactly.
So once you have embed CLI installed, which you can verify if it's working for you by running embed-help. If this command works, you have embed CLI installed. Congratulations.
So I installed it, but I don't know how to open it.
What OS? Windows?
Windows
Okay. Did you use the installer or the manual installer?
installer.
Installer. Cool. There should be a file on your desktop called run embed CLI. It's just a .bat file that will load up a little environment for you.
Missing Python modules.
Yeah, it was in the instructions of kind of pip.
Yeah, I did.
So you did pips too?
Yeah.
There was a certain version of pip too.
This is it.
I tried typing
PY serial.
it didn't like 2.7
Space.
No, it specifically says don't have 3.
Yes, you get access.
Okay, I was looking for something that's.
Nope,
It's
it's
just
just
it doesn't like
GLI.
you can run from the command line.
Okay,
cool.
next step.
So, once you've got it, embed import that link from earlier.
On Windows, 1.2 does not support Python 2.7.
The link from earlier.
It should be 3.5 or 3.6.
Well, I have that too.
So this is the link that was on the slides earlier. The github.com/microtensor/microtensor in this demo.
You using Windows? Oh, you don't use Windows.
Everyone got
So that
to
was
this
Windows.
page, right?
Okay.
Cool. We're just
So you're not using Windows, right?
we're just going to follow the instructions from the
Is that
README
Windows?
down
No,
here.
it's Mac OS.
Yeah, so it might be.
So following the instructions right here, we're going to run embed import and then pull in this URL. So Control C. And I'm just going to run embed import. Same thing, and you get rid of that at the beginning.
So can you do that?
So when you run this command,
Down.
it'll pull it down to your machine. embed import works by you handing it a Git URL or a Mercurial URL, and then it'll pull down all the project files down your machine. If you're curious, just briefly, it works off .lib files, which are essentially URL redirects. So you'll see like embedOS.lib in the project file, and that's just pointing to the URL where it's going to pull that from. So it can pull libraries or it can pull direct source code. In this case, it'll pull down everything you need to get this run. So once you hit run, it'll then pull down this folder right here called utensor mnist demo. You then cd into it. You should have all of the shenanigans. If you've got your board plugged into your machine, you can easily check that by saying embed detect. And sure enough, it's recognized that I've got the Disco F413ZH plugged into my board, or plugged into my computer. So I can say embed compile, it should be skipping down a bit. This is the command that you run. And when you run this command, it'll compile the binary and flash it to the board. All the stuff between that first command and this one I just scrolled past was for reference in case you want to know how to compile your own microtensor, or how to take protobufs, run it through microtensor. We're skipping over all of that in the interest of not bogging everyone down with installing Jupyter Notebook and everything else. I saw questions.
Embed CLI, when I tried to do the import, this is like I'm using Python 3. Do I have to care? Or?
No.
Okay.
As of embedOS 5.11.2, we made it backwards compatible with Python 3.
Okay.
So Python 3 should work until it doesn't.
All right.
As per the disclaimer with everything Python, it should work until it doesn't.
Yep.
This one is
HG clone error.
Say again?
HG clone error.
So you need to install Mercurial. If you've got pip, you can just say pip install Mercurial.
It can come as a Python package. Yes.
Running embed deploy. Actually, did you do the import first?
So you need to.
No. So there was an embed import.
Yeah, no, the last one.
Should be an embed import. Yeah, that was the. Yeah, the embed import was done.
All that stuff. Then if you have your own model that you want to train, those instructions on how to train those models.
Yeah.
It's a little bit beyond the scope.
So I've done it.
Then make sure that there was verification product like
Yeah. So he said, don't worry about Jupyter. So utensor CLI is that? Yes. So, I've got a question for you. After the embed import, I've got this thing hooked up. What can I do to test to just make sure that it's actually talking?
Run embed detect.
That's what it was.
So what's happening right now is it's loading the binary into my board, and it should be done.
Embed OS tools weren't found in. Well, I have to CD to your folder at that time.
So fun fact, this right here is the compile command. So embed compile -m is the target MCU that it's compiling for. In this case, the F413ZH. -t is the tool chain, GCC ARM. If you've got the ARM V5 or V6 toolchain or IAR, you could just as easily use those. I'm then using a profile, which is building microtensor. The reason we're using a profile is the default embedOS profile uses C99, and microtensor uses C++11. So different profile, literally just 2 digits change from 99 to 11. And then to flash it to the board, you just add -- flash to this. And check this out. This LED right here is going to start flashing. So that LED flashing means the board's being programmed. And after about 20 seconds of programming, because it's a fairly large binary, it then resets itself. And now it's up and running. So now I can, write my digit, press the blue button, and there the example code's running. Questions, thoughts, concerns?
So that's now ready to start collecting data.
No, this is running inference. So we have a model that has been trained.
Oh, it is.
The model has been compressed. The model is now on the board, and all that we are doing
And
now
local.
is running it on the board locally. Yes. And it's running that digit recognition software.
So now if anybody does a number, it should recognize it, transfer it to a digital representation.
Yeah,
Should.
in theory. We trained this model in about 50 minutes, and so there's all kinds of tricks that you can do to make the accuracy far improved. So, for example, we straight up took it and did a byte-by-byte comparison, which is not terribly accurate, to be honest. What we should have done is run the numbers through a fuzzifier and then compare it against those in an extra layer, so that if I'm off by a couple or off by a couple, it has that in its data set and recognizes. We were lazy though, and our computation was limited, and we were trying to get on a plane, so we didn't.
Fast and Furious.
Yeah, so the accuracy on this model today is about 75%, because I did it in 50 minutes. We have contingencies in place that we know we should have done that could have gotten it up to the high 90s in terms of percentage, or in terms of accuracy. We leave that up to the user as an exercise for the user.
To tweak.
Yes, exactly. My goal today was to show you how to take models that are far too big to run them on embedded systems. That's all I was trying to do today. And I should mention that all that stuff that I scrolled past, all the Jupyter notebooks, all the UTensor CLI, that is all how to train your data, or how to take your data and turn it into a model, and then how to take that model and shrink it down into a .c to .h. So if you'd like to step through that, if you've got someone on your team that you want to run through this, if you've got a really large model that you're trying to deploy, I've heard some people at lunch today saying that they had some models that were like 300 megabytes, and they didn't want to put them into their GitHub repo because they didn't want to force everyone to download it. Try microtensor. Should solve your problem pretty nicely.
Is there like a Docker hub for model repositories, for that very purpose?
So we're seeing a lot of data sets being shared through academia right now because we're at the forefront. We have yet to see a app store style thing for data sets emerge. Some people in academia will argue that it's not possible because each one is so specific to the thing and da-da-da-da-da.
That's like saying YouTube isn't possible.
Right. I'm still waiting for someone to build the app store for data sets so that they can charge a small fee and everyone else can get access to them.
Is it worth quitting my job over?
If you can make it happen, yeah. Honestly, yeah. That's part of the ecosystem that will enable ML at scale that is still missing.
Yeah.
Just that ability to say, hey, I want a 9-axis sensor fusion algorithm for a gyro magnetometer and accelerometer that can detect whether I'm doing a push-up setup or a jumping jack. I need that data set. Someone needs to have spent the 3 to 6 months doing a jumping jack and labeling it, and doing a jumping jack and labeling it. And they probably need to do it with a couple different sensors to make a generic data set. That doesn't exist, not open for free. I know a couple startups, each one has built it on their own at different points on the globe, and they don't know each other exist. And they don't know that they could be sharing data to curb their time to market. Someone needs to build that. Someone needs to come up with a way for data sets to be shared in a way so that the original creator can still make money on it. Still waiting. Other questions? Still waiting for someone to say they got it working.
58%
Downloading.
The Embed OS one?
Yep.
Yeah, that's what you get with university Wi-Fi.
Actually, I'm having an issue having it on my system.
Ooh, okay, what are you running?
Linux store.
Ooh, fabulous.
I'm not seeing anything in the labs.
Doesn't mind, but I don't think it has anything to do with the device.
Sure. You have plugged into one USB, sir. So there's two of them. This one is the one that plugs into program it. This is the one that you can plug a USB key into and then read off USB key to your device. So it's host versus host.
Did you read this? What's that?
Make sure you plug into the right USB.
They're all the same on
Right,
this.
No, there's two USB ports. One of them is clearly labeled ST.
Oh, well, look at you.
So the one that says SD link is the one you want.
Okay, well, so maybe all is not lost.
Indeed.
We don't necessarily have rights to those people. Okay, the lights are all lit.
Yeah.
You said get install material, or is that set up?
Psychedelic.
Ooh, we are in, brother. Okay, so now what am I supposed to do?
You can also check that you got
So,
You gotta do that.
So it should work with
What
500.
am I doing?
Put your hands over the ear, man.
Oh, I don't. No, Mercurial, you're right. Is only Python 2. My apologies.
So-
The embed OS tool should be Python 3 compatible. I don't
so
think
do
it's updated
the embed detect and it came up properly?
Yeah, well, yeah, I've got,
I can't just install material through
blah, blah,
Mercurial.
blah, it says support
So I think you're down to the embed.
And the reason for that is that it's pulling embed OS.
Correct?
No, not in OS.
Or do we
It's
have to
pulling
generate
the
code
graphics
Well, it
driver
seems like
from the ST page that is hosted in Mercurial on the embed OS
Yeah,
website.
to generate.
It's pulling embed OS and microtensor directly from GitHub.
Take that in.
So when you say embed import, it just transparently takes it and pulling it down no matter where it is.
Total buff distribution.
More, so it looks like there's more coming after the big embed OS.
Yeah, there should be 2 or 3 little small ones.
Coming, so just wait till I get it from.
It's installing it now.
I actually did do the embed deploy to fetch the necessary libraries. Like,
No, man, that's just part of the kit.
that,
So, this
embed
gentleman asked about
deploy.
the That is a 5 microphone sensor array. My intention was just
plain old embed
first,
display.
the low hanging fruit is the in this data set, because it was really easy, we could just grab the data set with those academic data sets that's widely
you
available.
comparing,
Pretty cool. Demonstrator
Oh,
point.
next. It is good. And then after that, you have to do the compile.
We'll be using the microphone array to make keywords.
Like you did up there.
Train it, 20, 30, 50 times, and then you try selling it off, on, and the LED will go off. That's the next step.
Right underneath.
Are you local?
Austin, from Austin.
Okay. When and where is your next,
In Minnesota?
Oh, there's one in Minnesota? No, Texas. I think it's one.
famous?
Yeah, you're right.
It's a little ostentatious, I know. but-
Get it?
It is the home of spam, surely you've heard of spam.
No, that's the top consumer.
Oh.
Big
Or
Austin.
Mel has a big pork processing plant down in Austin.
Is it Austin with an I or Austin with an E?
So,
I,
Oh, cool, got it right.
the copy and paste.
Oh, you
I see, I see.
Yeah, the invention file.
Jane Austen with the E. Oh,
So,
Austin from Austin.
when you do the microphone array workshop, would you do it on Google Hangouts or something I can join remotely?
Yes, so actually, funny you ask, if you go to youtube.com/farm and subscribe to the channel,
Or subscribe?
it's not there.
He did a flash
I
after
do
that.
weekly
So,
office
right
hours.
before
He
that,
did a
generate-
dash flash.
One of them, probably about 3 months, will be this work. We'll run it in person 2 or 3 times, and I always take them online.
So do the command in space slash
I
dash
call them
dash
in person
flash.
for a couple dozen times, and then I take it online and broadcast it to the world. That's my Netflix stuff.
There you go.
Our member, all one word. And we we try and do every week, sometimes it's every other week, like this week I had to cancel because of planes.
Embed.
So it doesn't like,
Embed.
Correct.
yeah, but the thing is,
It's a
in
little
the
weird.
instructions.
2 M's in a row, basically.
Yes, ma'am.
Oh, so it's
Jupiter
Jupiter
office hours,
notebook.
so we do other really
That's,
cool topics where we
step
have open Q&A from the community.
Or there, no,
So
we
if
gotta
you want
generate the
direct
embedded
access to our
system.
engineers, that's the best way to do it.
Okay,
Because
well,
it makes
that's
you get the technical expert.
microtensor.
Did you guys read the comments?
Live, yeah.
Yep.
We're super responsive like that. We leave the comments on and answer them all.
I mean, he really
Yeah,
did
the marketing tab, not like it.
Yeah, but the trolls don't care about
Flash.
that, right?
We've had a few.
Really?
Yeah, it's been great. I love reverse trolling. It makes my day when it happens.
So,
Because I'm allowed to. Like that's how you handle the trolls. You're
Right.
right.
sorry, yeah.
You ban them.
Embed polite.
A little bit. Otherwise, everything going good? Still downloading?
No,
Yes, sir.
Okay.
So walk me through this. I did an embed detect.
Yes.
Switch to my.
Yeah, it seems like it's fine now.
Can you show me?
just to try to get it on.
And then,
Straight to the bus.
okay, and that's this one here?
Yes.
Okay.
Now, did you install GCC again?
It's just whatever is,
Cool. Okay, so if you go back to the document, no, not that GCC. It's a different, all the way to the top.
the price says it's capped GCC.
Right here, mid-C line. Click on that. You're going to need to install the rest of it. Because there's a GCC non-EAVI, ARM non-EAVI GCC. It is the GCC compiler specific for projects. What the GCC you have is for compiling for the processor in this one.
Yeah,
You
okay.
need to install the GCC for compiling for that chip.
So I need to follow this.
To prepare the embed.
No, that's,
If I may, I'm going to help you out real quick. There's one thing, unfortunately, he built this a while back, so I'm going to just bring you up to do this. Okay, so you're on Magic, right?
yep. Okay, so we just go there.
And you can either download this massive thing or you go back to the manual install instructions and just install GCC. Because you've already installed it, it's live and everything else.
So where are those?
Right here, install manual. Yes, sir.
Oh, okay, so it didn't get downloaded initially.
Install it in Island. Linux instructions.
It's not closer, so it's like a hydrant over there.
Yeah, you're looking at Linux.
That's what we were thinking.
Sorry.
Requisites. So real install. So go to this page.
I'm just trying to get the one.
Highway versions. This is ARM compiler C6. You're going to want GNU ARM embedded. Because everything else requires cables.
Okay. And I work for a big company, we don't pay for any of this.
I know, it's great, isn't it? Don't you love it when they like give you the hassle about your travel expenses? You're like, oh, it's
Yes.
$10. So cool. Short it up. So it's going to be. You're just going to want to install that community.
It'll take a while with that Wi-Fi.
Yep. So once that downloads, you'll need to put it somewhere, and then there's instruction on the previous page about adding it to your path. And once it's in your path, it should just magically.
So next year you're gonna be giving us one now, as well as to everybody, right?
Only if sales gives me budget for it.
Yeah. Isn't that what they're here for, is to buy these things for us, right? I'll stop if I get. Yeah, there you go. Good.
Good.
This is the default ST application.
Sure. When we flash the new stuff.
You know how to do this? Do you know how to use it?
That's what I was thinking.
Before when it was dead.
I'm like, I don't know. You could talk to HR and, you know,
Okay, so then we say embed detect.
Does he have an analog?
And some going? Or that's the default?
So because I'm in the CRI, so then
Sorry about that. My installer told me to use the I really didn't maintain that. So we got actually
Well, that's basically
Fedora.
The end there is like
What I need to do is do
Specialized. That's what I said, the RAM was like, I think my first computer had that much RAM.
Play with it. And so between each run, you're going to need to reset it. And blue. So black to reset, blue to run it. So black, draw, blue, reset.
I think this is slightly.
So okay, now draw your like I said, accuracy is
I was trying to
Totally
remember what
forgot.
that
Is
is.
that just
bad at drawing, that's all.
But I can show you this one.
But I was trying to do an 8.
What if you do this?
The early Macs, they ran on the Motorola.
Well, yeah, I mean, come on.
So this is where we get into
You might as well just etched
Yeah,
it in the
that's
screen like.
Yeah, 68020.
this is still pretty cool, right?
Yeah, I'm just
The 68020 was 16.
So does it make a difference when it's
Yeah, but the 6800, 68,000.
Machine learning is all about taking massive data sets,
Well, I'm not
finding
sure about
patterns
that
in them, and
because
doing pattern
remember the
matching. At the end
68,000
of
were
the
all
day,
memory mapped out.
depending on how you write your
So they
algorithm,
had
it's
more
either a glorified pattern matcher, or you've given it an algorithm that draws a line on a screen. And if the data's on one side of the line, it's one thing, if it's on the other side of the line, it's another thing. That's essentially what ML boils down to at its core. For audio recognition, you're probably going to have a couple of different lines running to try and figure it out, to find out like S's, pitch, and things like that.
So like we have people actually real intelligent, but not necessarily people who come at machine learning and systems. So if I'm able to say, give me this, and give me this, and I just take this and run it through. That's kind of what I'm trying to remember. And whether this is changing dogs to dogs or audio to audio, some kind of text.
You're going to need to work with them to specify. So there's going to be two engagements with the data science. You first have to engage with them to define what the parameters for judging your model and how you're going to collect your data set. So for the audio, is it 192 kilohertz audio? Is it 32 bit audio? What is the audio that you're going to
That'll be my input device.
Right.
Yeah, because you got levels.
Right. So you lock that in, you have the levels correct, and then you generate from them a bunch of different examples. Then they take it, do magic processing, come back and say, here's your graph that we think works best based on what you gave us. And if you run it through microtensor and run it through.
Yeah, that's kind of what I want. Is I don't know when it's doing stuff. I'll just take whatever I run it through other.
I have a magical guy who lives in San Jose who speaks like 12 words of English, but is a machine learning just genius. And we literally interact through block diagrams. Say,
What,
this
you
is
know
what
what
we're
path
doing.
we're supposed to be on?
Give me this thing already here in the middle picture.
And
that's how we built
it.
Completely different understanding of the world. Don't even really speak the same English. But we can engineer together by defining the inputs and the outputs. Sure. And so it really is two different things. Okay. Anybody else?
I don't think you guys companies would like to crunch this kind of stuff.
Yeah.
Yeah.
Configure this for cloud.
And you guys got the information too to show. I mean, like we were just talking about, it's all about the data sets.
Oh.
Okay. Yeah.
Good.
I was talking to a guy that worked at a company, and he was taking pictures of corn stalks. Yeah, that should be the leaves, specific to leaves. And he said, we can like 5,000 pictures. And they had different stages
Oh.
because they had classified.
It's probably because
They
they
can
can
literally
space
now
it
take a
right
picture
there.
of porn star and know if it's
Okay.
Yeah, it doesn't, it's having issues with the space.
They better work.
So if you just fold it out,
Happy hour will be downstairs.
that's what it is, the folder out of your name, because your name
Just in Windows?
yeah, just move it to C/users or something. Because there's a space in your name, that's having
You
issues.
don't drink?
You need for
I'll be okay.
it's probably because it's not that
stuff. Yeah, and it's cool stuff, but it's like expensive. Fun is done at most of the money. You are,
So mid-CLA is
My wife said I can stay up till
Del
like
Monte
8:30.
or something.
Yeah.
It's just one program.
Right.
Yeah.
Unfortunately, Shell hands it.
If you're even
It
2,000
doesn't
acres or less,
space escape,
you know.
space
Kind of like
There's
those
some-
little top things around.
Well, on a day like this, heck yeah. Winter, not so much.
Yeah, like you go find that folder, just move it up to the global, so you'll be good to go.
Oh, wait, no, that's.
You got any questions? Did you get my contact info?
Was it? Okay.
Okay, everyone's still moving along, slowly but surely.
But do you know that you can't work on your own kind of, it's funny,
I think it
you can't work.
was, well, I mean, you saw them setting up those catering, changing dishes downstairs. I assume they're gonna have
Specifically,
snacks and beers.
Their
But
machine language that is running on those machines, you know, farmers have always been notorious of tinkering stuff.
So
Illegal.
it looks like everyone's starting to either get to the point where they've got it just about running, or some people have kind of zoned out of it and are doing their own now. So this is now the part where I open it up and say, I would have had a really cool demo right here, where I would have hooked it up to the cloud, sent training data up, and showed you how to then compress a new model and send it down via firmware update. But again, I got sick for 7 days and there went all my development time. South Korean flu. I thought I was going to die in a foreign country that didn't speak my language. So now I'm going to open up the floor for you guys. Does anyone want to talk about something they're working on? Does anyone want some guidance on something they're doing, some best practices? I'm not going to claim to be the world's greatest expert on this, but I've done probably a little bit more of it than anyone else in the room has. So I'm happy to talk and share and offer guidance or help. Or we can just brainstorm some cool stuff, because I'm down for that too, and stealing ideas is great. Yes, sir.
IoT architectures typically, a lot of times they have a gateway
Yeah.
in between the cloud and the end node.
Yeah.
When you're doing OTAs with these 32-bit processors and there's a gateway involved, how good is that? Is that something you guys support? Do you have a gateway intermediary that kind of just bridges that, brokers those things together?
So there's a bunch of different ways you can do it. The way that our solution is architected is it currently assumes you either have an IP-based device, and if you have an IP-based device, it's really easy. It says, hey, IP device, you want firmware update? Yes, okay, cool. Here's the manifest, here's the file you need to download. Here's the check file you need to run. Go download it. And so then the end device that is IP-based will then send calls out to the internet, pull down the new binary, put it in storage, pull down the manifest, run all the different hash checks that it needs to, flash it in and restart. So for Wi-Fi, Ethernet, cellular, NB-IoT, and 6 low band/thread, super easy, all IP-based, they can take care of themselves, they don't need a gateway. If you're putting a gateway in place, it's usually to just give them an IP bridge, because you're sitting in the middle of rural America and there's no Wi-Fi, so you get like a cellular backhaul, but for all intents and purposes, it's an IP connection. For non-IP devices, it gets trickier. Non-IP devices, each and every time you want to implement FOTA or some sort of bulk transfer, it has to be custom, because most of them don't have their own definitions. So for non-IP, we're talking Bluetooth, LoRa. Got anything else you're thinking in particular?
No, that's what I was thinking. Yeah.
Okay, so for Bluetooth, we have a solution. We've got a embed edge gateway thing. It's essentially, you're running Linux on a gateway. You just are, because that's what's free and cheap, and everyone loves free and cheap and relatively stable. If you run on Linux, that means that you can run arbitrary script execution. We've got a gateway solution called Embed Pelion Edge, I think is, where's my sales guy? Sales guy. It's called Pelion Edge now, right? Pelion Edge is the correct keyword to Google. Pelion Edge is essentially a gateway solution. It has this translation protocol between BLE and the gateway, and you're allowed to implement your own thing. Because with BLE, usually you're doing custom profiles at that point. We have a suggested implementation that we have that works. And so if you implement this profile on the device and this config file on the gateway, they can talk and check and exchange hashes and exchange files. It may not work best for you. Maybe you want to power optimize it, in which case you can mess with it and do that. For LoRa, though, LoRa has this interesting thing that's coming out where part of the specification it's adding firmware updates. The BLE SIG is a little slow. They've done a great job of optimizing for audio, even video, but the whole IP spec for Bluetooth fell apart a year and a half ago now. So they never really got on that game. LoRa, on the other hand, actually my boss, Jan, is part of the LoRa SIG, and he's been driving firmware updates as part of the spec update coming out in 1.2.
Really?
Assuming they ever get it out the door, because they're going through the final certifications right now, firmware updates will be part of LoRa. It's why they put in LoRa Class C devices. Do you know about ABC classes?
No.
So ABC classes in LoRa, A is the traditional LoRa device, super sleepy. It wakes up, it sends data out, you've got like a 30 millisecond window to then piggyback data back down the channel, and you only get about 30 bytes. That's what we had since 1.0. In 1.1, they revved it and added Class B and C devices. Class B devices are essentially time sync devices that wake up on a set schedule and phone home. These are good for getting consistent data reads, but more importantly, because LoRa is a one-way broadcast and a piggyback back hop, it gives you a defined chunk time for when you will next be able to send data down. And then there's Class C. Class C is supposed to be always on, hooked up to battery, and it's just transmitting constantly. So it actually has like no lossy connection that's usually associated with LoRa. Okay. But it has to be battery powered. You can't, or it has to be wall powered.
Wall powered.
If you plug it into a battery, it's going to kill your battery lickety split.
Unless it's a lead acid car battery.
Even then,
with a solar panel.
But for all intents and purposes, that's wall powered.
Yeah.
Fun fact, that Class C was added so that we can do firmware updates, so that your device usually is in Class A, super sleepy, low power. When it sends data home and then the server says, hey, I've got a firmware update for you, it goes, all right, 1 second, knocks itself off, comes back in Class C mode, and goes, all right, give me the data. Okay. You then get that massive downlink where you can just chunk data down. Once it's done, it'll then apply the update, restart, and go back to Class A. This is also why, as part of the 1.2 spec rev, they're recommending that for any LoRa deployment, you don't just have one gateway, you have minimum 2, preferably 3 gateways. Because if you've got a lot of devices, you need 2 gateways, otherwise they're talking over each other, and then 1 gateway dedicated just to firmware updates.
And all those other nodes have to wait for the firmware update.
Right. Which is why you need a dedicated gateway for the firmware update, otherwise you're just going to blast over anything else.
So inside a photo though, if we're talking about sending retrained data back up, and then you're probably going to expect to pull down weights and models at some point. What protocol, if it's an IP-based node, is it MQTT, HTTP, CoAP?
CoAP mostly.
You guys?
We like CoAP. Our device firmware update services run off of CoAP because that's what our client uses. Who here is familiar with the difference between CoAP and MQTT? Just out of curiosity. You know what's up. Anyone else? You kind of know what's up. So for reference, everyone knows what HTTP is, right? You've all opened up a web page and looked at the raw data file. Those are all in ASCII encoded characters, right? You can read them. They're human readable. The smallest denomination of data you've got is usually 8 bits if you're using ASCII. If you're using Unicode, you're up at 16 usually, or especially Unicode 8 bits. It's usually 8 bits, right? That's the smallest. So if you want to send to 0, it's 8 bits. That's great if you've got a super high amount of bandwidth and a large processor, and bandwidth really isn't a concern like it is on Wi-Fi. But if you're on a small embedded device going across a lossy connection with very limited interface, you don't want 8 bits to be your smallest amount. You want 1 bit to be your smallest amount. So you need to do a binary encoded protocol, which is what CoAP is. CoAP compared to protocols like MQTT, which are also ASCII encoded under the covers. They're not binary encoded. CoAP, bit for bit, sending the same amount of data. CoAP will use less data to send the same amount of data because it's binary encoded. That said, it's not human readable. So if you try looking at a CoAP message, you need to run it through a decoder program, or else you've got no idea what's going on. Unless you're one of like the 3 people I know who read the spec and have memorized it, and they're a little crazy now. So in general, CoAP tends to have, you save somewhere between 30% and 60-70%, depending on how much data at once you're sending and what type it is. But it does save a significant chunk, and that is important because for battery-powered radio devices, that means less data being sent, which means less battery power being used, or if you're over cellular, literally less money being spent on sending that data.
Not to mention the TLS overhead is small.
Fun fact, you can do DTLS using UDP instead of TCP and get it even smaller.
That's what I mean with CoAP, it's using DTLS, shrinking that overhead.
Our implementation allows user configuration very, very bluntly of using UDP and DTLS or TCP and TLS. And that's because, fun fact, UDP does not work in China.
What?
Once you're behind the Great Firewall, UDP bounces around and goes nowhere. You want to use it inside of China, you want to get something over the GFW, assuming it's not something that they're going to try and actively block, you got to use TCP.
So you do CoAP over TCP there?
Yeah.
Oh, okay.
And that's the only way to get it to guarantee get out. And even then, you can have, I kid you not, a 10-minute delay. I've seen packages bounce around inside of mainland China for 10 minutes before they get out, and then another anywhere from 5 to 10 minutes before they come back again. But because it's TCP, it works.
Okay.
Connection based.
Yeah. It'll keep trying until it gets that connection, that handshake happens, and then it will close it. If it's UDP, though, it just does a single broadcast and hopes it gets there. And inside of countries with heavy firewalls, that doesn't work.
Thanks.
So I like CoAP, especially because it's smaller. You can run it using embed TLS, doing TCP or UDP.
I can't figure out why it hasn't caught on.
Honestly,
Is
because
it young or?
the upgrade cycle, CoAP's been around, what is it, 5 years, 8 years now, effectively. It's probably got another 3 to 5 years until it's included in every server distribution by default. Right now, there's like 3 or 4 servers, but you have to manually install it as an add-on package, unlike HTTP, which is just there by default. So until it is there by default, it's the power of the default choice. MQTT is so popular, not because it's the best protocol. It is computationally a protocol that has serious problems with it. Like, there are massive issues with MQTT in terms of inefficiency and some security bugs. But because it's been around forever, you can pip install it on any server you want, and there's tons of docs, which is why everyone based off of it. Not because it's the best, but because it's the lowest common denominator. Again, it's the Betamax versus VHS thing. It's not which one's the technically best solution, it's which one is the most popular with the widest adoption. But we are seeing that change now. Over the past 3 years, I've seen CoAP go from being the serious hardcore nerdy thing to actually showing up in like the main
Make video on it.
Yeah.
People might start to listen.
It's going to be interesting.
Yep.
Yes, ma'am. Okay. Anyone else questions before I troubleshoot?